Yes, I can hear you very well.
Okay, great. So we just need a couple of minutes. Our tea break is almost over. Then we will invite questions and start. So we were collecting names who would like to ask you questions. So we have some names. I mean, for both of you, Ashok is here. So can you zoom out a bit so that Francesco can see Ashok sitting here? Okay. I mean, like he can see me. Okay. Him also. Not okay. Him.
It's fine. It's fine. It's okay.
Oh, sorry. All right. So, yeah. So after that, I mean, initially there are some names we have. They will ask questions, and after that, it would be impromptu. The audience, they will introduce themselves and ask questions. Okay, Ashok?
Sure.
That is how we are doing it. Okay, I need a few more minutes. Just another 1 minute. Another 1 minute. All right, so we start now. The discussion session, I again begin with thanking both of you, Francesco and Ashok. You did a wonderful job. Now the questions, for Francesco, we have one question from Orijit Chatterjee. You're there? Yes, please. So please focus on it.
Yeah. Hi, I'm Arijit from ISER Pune. Hi, in your tripartite setting with the reference system that you talked about there with respect to complete positivity, that reminded me of the choice formalism of choice isomorphism, where we again use that reference system and we apply the map on that correlated system. So that correlation has a key role to play there. So is there any connection really, or so that I want to know about? Yeah.
Thank you very much for your question. Yes, indeed, there is a connection. There is a very strong connection. Just let me maybe share again. This is going to be fine, even though even if I don't enter into presentation mode, should be okay, I guess. So the picture, where is the steerability idea? So something like this. So yes, indeed, when you have the Choi isomorphism, also there, the basic idea is essentially that with a maximally entangled state between a reference and your system, you can steer any state of the system by performing some measurement on the reference. So the Choi isomorphism tells you that in order to understand properties of your channel, of your map, you need not go through all possible inputs, but you can replace all possible inputs of the system with just one maximally entangled state. The point here is that you want to start from the correlated states of the system with the environment. And what I was saying before is that this initial condition that is given by the correlation, so the starting point, so the important takeaway message from the viewpoint that I proposed you before is that the starting point is given by the initial correlated states that are allowed between system and environment. So once you fix these correlated possible initial conditions, then the set of states that are allowed, that are accessible to your system, are restricted. So in a sense, it's like an extension of the Choi isomorphism in the sense that now you don't require anymore this maximal entanglement to be there between reference and system because you need not span through all possible states of the system, but you're interested only in those that belong to the set of initial conditions from which you start. So I don't know if this answers.
So here the reference mathematically plays the role of selecting the right set of system environment a system that can be steered from R, right? That's what you're trying to say.
Exactly, exactly,
Okay.
and no more than those.
Yeah.
Because you start from that initial condition. Whereas the Choi isomorphism essentially starts with the idea that the system can be initialized in any state possible. And indeed, actually, this formalism contains the Choi isomorphism because if you require that your system can start in any state, then the only condition that is compatible with that is exactly the Choi-Jamiolkowski. I think I put it somewhere. So here, yes. So if you want that the possible state, the accessible state of your system coincide with the entire state space for your system, then the factorization condition is the only one that works.
Right.
Which means that you are in this situation here. In this situation here where reference and system are, the state is described by a maximal entangled state, and then there is some state of the environment which is just there in tensor product form.
And I have a second question. Can I ask here now? Okay. So my second question is slightly pragmatic. I'm an experimentalist, so slightly pragmatic. That if I think of in terms of recovery of correlation, so I can think of a local bath and system is embedded in it. And let's say that bath is R in this time and the correlation gets delocalized. I want to recover that. So this initial conditional mutual information between R and E given Q, that can set a bound on the amount of mutual information that can be recovered in the later time, because if that is 0, then there is no revival, right?
Exactly.
So is that a bound?
The amount of information that can be recovered is exactly equal to this amount.
Exactly equal. Okay.
So in the worst case where the entire information flows from the environment back into the system, the maximum violation of the data processing inequality is given exactly by this quantity, which will be non-zero. It will be a positive quantity. This gives you the maximal violation of the data processing inequality, the local data processing inequality. Yes.
Thanks.
Exactly.
Thank you. Our next question is from Dr. Manik Munik. This is again for Francesco.
Hi, Francesco. Yeah. Nice
Hi, Manik.
talk. Yeah. So before moving to my question, first I would say probably very soon you have to visit us, because as a reporter you will get a nice coffee mug. You have to collect that. So in your talk you beautifully give the history starting from Pechukas and this Shabani leader. So, but after Shabani leader 2009 paper, this Professor Simon and his collaborator, they come up with a theorem that what Shabani leader claimed that this system environment that allows a quantum zero discord correlated state to be the system dynamics to be completely positive. But Simon and their collaborator, they claim that not only means even no correlation is allowed to be the system dynamics to be completely positive. Can you just shed on light on that, their result?
Yes, actually, so there is, you just sent me the paper by Simon, so I can share the PDF. Yeah. So this is like a prepared, well, I just had 30 minutes to prepare the answer. So let me share the paper by Simon and collaborators, because I think it's very relevant. Thank you very much for the question, by the way. So I need to stop sharing this and I need to share another window. It is this one. Okay, so here is the paper by, is this paper by Savapati, Ivan, Ghosh, and Simon. Quantum discourse plays no role. So here, they still start somehow from this assignment map formalism. And basically what they tell you is that if you want, okay, so I think that the main result is here. So if you want that basically your system can be initialized in any pure state, then there are no other possibilities than the initial factorization condition. I would like to say that, so the problem with this assignment map approach to the description, for the description of initial system environment correlations, is that it starts from the system. So let me, I want to go back to my slides for a second, because this is an important point. It seems to be like a very marginal thing, but it is not. So in the assignment map formalism, you start from Q, okay? So you start by choosing a particular set of states of Q, and then you want to have this lifting that brings those states up. They lift those, that lifts those states to bipartite states. And you want this to be consistent, so that from this state you go back, if you take the partial trace of the environment, you go back where you started from. The preparability approach instead starts from here. So it just flips these two arrows. So the starting point is not the set of state of the system. The starting point, what I argue, what the starting point that one should take is the set of initial correlated states. And then you can, of course, you can construct the set of states accessible to the system by taking the partial trace. And if the Markov condition is satisfied, this tells you that there exists a recovery map that brings you back from Q to the state you started from of the correlated system. So starting from here, going up and then going down, poses a lot of constraints, right? Because, for example, you don't want that the same state here corresponds to two different states here, no? Suppose that there are two states in the correlated system whose partial trace is the same state. Then in Simon's paper, they argue that, of course, so I start from this state, but I have two ways to lift it up. So if I have two different ways to lift it up, then this state could go through two different trajectories. So then it means that this is not a map. This does not satisfy consistency, right? But because they start from the system, instead, if you say that what is given by the physical problem is the set of correlated states, that's where you start. The joint evolution is uniquely defined. You have one correlated state that evolves jointly. The question is, if I go down, and this could be a many-to-one map, of course. So many correlated states could correspond to the same state of the system. This problem disappears, because then you have compatibility by construction. So it's just flipping the start, flipping the two arrows, but it makes a whole lot of difference from the conceptual viewpoint.
Francesco.
Thank you.
Thank you.
Now some questions from audience for Ajoy, Ashok. The first person is Vivek Sabarat. Yes.
Hello Ajoy, I'm Vivek, I'm from ISER Pune. So the question I have is, to increase the relaxation time, we used there some sort of a pulse sequence I saw. So what I didn't understand is, if we are using such a continuous sequence of operations to increase the relaxation, how is it going to be useful for us? Because we have exhausted all the control on the spins by using the sequence. So how are we going to make any other operations to make use of this relaxation, increased relaxation?
Yeah, well, so it depends on the application you have in mind. So the application that we are heading towards is sensing. Data I showed you, and I didn't show you lots of other data, but so it's okay. Yeah. So if you just consider the sensing example as an exemplary case, then you can keep the spins alive for a long time but then also they report on the field that they're exposed to. So you get the lifetime increase, but then the spin state moves in a time-dependent fashion that carries a direct imprint of this field that you're trying to measure. And for sensing, it matters how long you can measure, because as you might know, the longer you can measure, sort of the sensitivity improves as square root of time, and the longer you can measure, the more sensitive you can make it. Hopefully that answers your question. So this is not quantum computing. So indeed, you are applying some control sequences to keep some state alive for a long time, and the question to ask is, what can you do with that state? And for sensing, definitely you can do stuff.
Yeah, thank you. That answers my question.
More questions for you, Ashok. Next one is Shayan Shengupta. Yes, please.
Yeah, is this stabilization related to the quantum Zeno effect, where you measure the state repeatedly to sort of preserve it and prevent it from dispersing?
Yeah, so here the measurements are, you can consider a weak measurement. So there's no back action of the measurement device on the spin, very, very weak back action. So it's not a Zeno-like phenomenon. It's what I showed you was not a single spin, it's an ensemble of spins, and you're very weakly coupled to a cavity in a very weak coupled limit, and so then you can sort of listen to the spins without disturbing them. And so it's not a Zeno phenomenon.
May I add a comment here? Like the spin locking experiment that you were describing in NMR, compared to standard quantum mechanics, so you have psi, you measure an observable, and the bond rule follows, so the system will collapse to one of the eigenstates with probability, which comes from the projection of the initial state to this particular final state. But in NMR, when we observe experimentally, we do not see collapse in that spectacular fashion. It is like a collection of spin system there, going to equilibrium, the coherence is dying. And you see that you can observe that exponential. And the observables are like sigma x or sigma y. But the system, when it goes to equilibrium, it is going back to the Gibbsian distribution. So coherences, I mean, you would expect POVM says that it should be one of the eigenstates of sigma x or sigma y. No. So there is somewhat interesting thing, because their case, I mean, like they are looking at the spin locking. So when you do the spin locking essentially kills off the error induced by the pi pulse. And it is immediately when they detect, at that time the spin locking is not on. So this locking field, it does somewhat akin to probably the measurement, but not in the traditional sense. No. But I think we go back to the question that you had, Shayan Shengupta.
Okay, sir. So my question to you is, the sequence, the pulse sequence that you're using, that's basically a dynamical decoupling scheme. And traditionally, sir, we use what we have read in literature is the Carr-Purcell scheme and the Han-Eco sequence scheme that we use to decouple the system from the environment. So what kind of sequence are we using here in your system?
So this is a variant of the Carr-Purcell. So in the CPMG train, all the pulses are pi pulses. It turns out a pi pulse is very bad in a dipole system, because the dipole Hamiltonian is invariant to pi rotation. It's very easy to show that. And so if you apply pi rotation, nothing happens. So when the dominant decay is not because of dephasing, but actually dipole interactions themselves causing decay, then if you apply pi pulses, nothing would actually happen. So here we are applying any angle but pi. So you can apply pi half.
Okay.
And in these experiments, we are applying 10 million pulses, all identical. But in new experiments, all the pulses are made different. You can make each of the 10 million pulses different. You can also do feedback, so you can measure and then change the next pulse based on what came before. And there are all kinds of new tricks that one could play with this 10 million knobs that you have.
how do we choose the optimal sequence
Yeah,
for?
good question. I don't know. Yeah, yeah.
Okay.
It's a question I think some theorists can try to. It's a strong function of the noise processes that the spins are exposed to. And, you know, I showed you this 800-second, very long lifetime. We don't know why it's so long. And you can say that it will become longer. It's very hard to predict how long it would get. And mathematically, estimating from first principles the extension factor is a very difficult problem. You need to know like information about the spectral densities, etc., which you don't have access to usually.
And sir, one more question. Sir, regarding this, if I'm using a few body system as our sensing system, and if it is in a dirty environment, it's interacting with all the spins. Now, if it's interacting with all the spins, the part which we consider as the environment, apart from the system, the part that we call the environment, we do not know how it couples to the system. We do not know the coupling constants, right? So it might be that some might be interacting strongly and some might be interacting weakly. So there can be a Markov and a non-Markov mixture in the environment as well.
Sure, yeah.
So
yeah,
how do we find out all
Yeah,
those
so
things?
here we have an ensemble of spins, so indeed you have like a distribution of couplings. But I think a variant of your question is interesting, which is how do you make sure that you detect the sensing field but not
Yes.
every other field? You know,
Exactly.
so it's all the thing is like we are sensitive to some types of fields, so these are time fluctuating fields in the z direction, like very specific orientation and frequency dependence, and we're only sensitive to those things, and every other thing is sort of cancelled, and that's how you maintain. That's why you can measure for a long time and still be sensitive to something.
So in this experiment, can we use quantum state tomography to find the final state?
Yeah, so you know, as Rangit was saying, in these experiments, you're actually using spins that are still in like what they call a high temperature limit. So it's not pure states, right? So they are kind of impure, heading towards mixed states. And even when you polarize them very highly, even then we are still like, you know, polarization levels between 1 and 10%, and it's still sort of a high temperature state. So we still represent the spins as a density matrix. And the measurement in NMR is very specific. You can only measure like summation sigma x or summation sigma y. It's very difficult to get like more difficult operators or different operators that you can get, for example, in a quantum information processor. And so, you know, so it's not very helpful to do. You can possibly do some kind of tomography of those states, but it's not very helpful. In the end, the sensing information is encoded in the sigma x, and that's what we measure. But what I want to say is this dirty thing is actually a very important point in my opinion, because while you can make the most pristine quantum information system, and it's often you're going to be in a dilution refrigerator or in a vacuum chamber, you know, isolated from everything else. And that's great if you want to make an excellent quantum information processor, you're trying to perform Shor's algorithm or something of the sort. But we are actually interested in sensing. So we are interested in sensing other things, magnetic fields from other objects. And there, by definition, you would increase your scope of applicability if you're operating at room temperature, or if you're operating inside other materials. So the advantage of these systems is that they operate under these conditions, and then they become naturally, you can sense other things because they're interfacing with the outside world.
Okay. Sir, how do we rule out that the field that we are measuring, it's not the background field?
Yeah, so it's a good question. So there's nothing in the diamond that will produce like a very specific signature at like 100 hertz or something, you know. So you can tune based on frequency, or the type of noise that you're trying to measure. But definitely, you need to have some prior information of what is the kind of thing you're trying to detect. Does that make sense?
Thank you,
Okay,
Shayan.
sir, one more.
So,
Sir, in superconducting circuits, we have seen that cosmic ray 2 induces error. They produce quasi-particles, right? So, do they play a role here?
Not in our experiment. So there, you know, you have this poisoning of the superconducting state by these. This is not directly operational in our experiments. We have much more dominant noise processes that occur at much faster time scale, so we don't even get there.
Okay, sir.
Yeah.
Sir, I have a question to Francesco, sir.
Okay.
Yes?
I had some question to Francesco, sir.
Okay, but let's move around a bit in the audience, and then I think our next question will be from Dr. Manavendra Vera.
So I will have one question for Francesco and maybe another for the Ashok. So I start with Ashok. Hi, Francesco. I still don't understand, because you say that you are thermalizing your system, right? So this is one of the typical question we ask, that how system thermalize in open quantum system. But at the same time, you are introducing pulses in the system, which I consider from a quantum thermodynamics point of view is like putting some work, right? So in which sense you say it is thermalized? If I say no, it is a steady state. Or on the other hand, if I ask that whenever you have this your rho to be proportional to e to the power minus beta H effective, how do you determine beta?
How do you determine beta?
Yes.
Yeah.
Is it? Yeah, please.
Yeah, good question. So, yeah, so this I think this issue about how does it thermalize? What is the exact the mechanism by which the spins thermalize into this effective Hamiltonian? I would say, as an experimentalist, I still don't understand exactly how this happens. I mean, we can have some hand-waving explanation, but practically, even with simulations, you need a large number of spins to be able to actually see this happening. But a simple-minded explanation is that even if you were to just take the simple example of putting spins in a magnetic field, when you put spins in a magnetic field, they thermalize into the Zeeman Hamiltonian, but also the dipole Hamiltonian that couples the different spins, gets truncated to commute with the Zeeman Hamiltonian. They call this a secular approximation. I guess Rangit will know this. And so effectively, again, you're creating a state that's thermalized to the Zeeman term plus the dipolar term. And it's in a similar fashion, we are achieving the same, but in a different axis. So we're imposing the effective Hamiltonian, and the spins are effectively thermalizing to this Hamiltonian, except the difference is that this effective Hamiltonian is imposed only to some order, because you're applying this pulse sequence, and it's very complicated to evaluate this Hamiltonian to many orders. So often we truncate in the 0th or first order, and then you're thermalizing to this. Yeah. So the exact mechanism by which it happens, I think, is a more deep question, which I'm not completely able to answer.
And how about the temperature? Is it like the room temperature or something else?
No. So, as I was saying before, you start with the spins in the high temperature approximation. So the beta is inverse temperature, and the temperature is usually quite high. And it's approximately the same order of magnitude temperature that you have in this inverse beta, if that makes sense. So
yeah, so its order would be same, but may not be exact.
It may not be exactly the same, right? Exactly. Mm-hmm.
Okay. So for me, it would be more like a steady state then, no?
I don't know. I don't know.
Maybe you just check some current.
I don't know what you mean by steady state. So indeed, the state is very long-lived. So I guess you can call it a steady state. But indeed, if you actually plot it on a log scale, you do see that it falls into this plateau and will remain for a long time. Maybe Rangit, you have something to.
It's a driven steady state. I mean, it's a prethermal state.
Yeah. So I think it's
prethermal
okay.
state.
Okay.
I mean, like there is this coherent Hamiltonian, so it's not full thermalization. So I mean, like if you remove that coherent state, it will thermalize. Okay, but then why the prethermal plateau arises, understanding that itself gives us some clue to understand full thermalization. So there are many approaches. One popular approach is you take a many-body system and you do Floquet, many-body coupled big system, and you do Floquet. So essentially, if you ask this question, like suppose I have isolated system, no bath, no nothing. An isolated system, how does it thermalize? It's like box of gas, you puncture, and then the room filled, and that we all know. I mean, so NMR analog is like you take a series of spin, put some initial state, and you drive coherently, or some kicked driving, and nothing else. Then what do you see? So in this case, as he mentioned, T1 is very long. So whatever he sees, that prethermal plateau, it cannot come from the regular relaxation. There has to be some other dynamics, because if you think that system bath coupling is the responsible for this reaching prethermal plateau, they have widely different time scale. This is happening faster, and that is much slower. So this is an enigma. So what he tried to do, I mean, like all these spins together, coupled, this is like an isolated system, because the coupling to the bath is very weak. Now he does this periodic driving exactly like the flow heating of the system. But instead, it goes to a pre-thermal arrest.
Yep. Thank you. It answered my question. So now I come to Francesco because, so whenever we talk about, let's say, open quantum system, obviously one of the desire is that to find the dynamical equation, no? Like Lindblad-like master equation. And there, we often consider this Born-Markov approximation where we more or less kind of approximate my joint state to always remain in product state, no? But obviously, this formalism that we are talking about, it goes beyond that. It says that, yes, my system and environment can have some correlation. Obviously, it has to satisfy this conditional mutual information or beyond whatever you have discussed, right? It has to be 0. So do you think if one replace this Born-Markov tensor product-like approximation while coming to this Lindblad equation and replace it with, let's say, our conditional mutual information to be 0 to start with, not the squash one, but the normal one, do you think would be able to get to this Lindblad-like master equation?
Thank you very much for the question, Manab. I don't know. Like, you know, one of the, it seems to be, you know, this, if you see how the Gorini-Kosakovsky Lindblad-Sudarshan equation is derived, there are very, very strong assumptions on how the bath is modeled. And, you know, you can imagine that there has been an interplay between what you can do analytically and give an interpretation on these conditions from the physical viewpoint, right? But if you leave behind entirely this Born-Markov approximation, I wouldn't know to which extent you can really push this algebra that they used to derive, that it is usually used to derive the Gorini-Kosakovsky Lindblad-Sudarshan equation. So I don't know. I don't know whether there could be a good way to incorporate that in a differential equation like that. Here, as you know, like also in our paper, we are considering only some discrete time steps. No, you start from a condition, and then you have this unitary evolution that happens like a black box. So you don't care how it goes on in time. And I wouldn't know how to open that box, actually.
Actually, just to make a comment on this also, because although the question I have asked, I also don't have answer to, but the reverse question somehow indicates, in a sense, the answer to the reverse question, saying that if I have, let's say, Lindblad master equation and there is a dynamics, I can have a recovery dynamics, essentially. So that already says that in every time step, in principle, I should be able to recover my environment in such a way where the conditional mutual information will be 0. Although one has to still look at in the forward process, the forward question I have asked, whether it is possible or not. So this is just a comment.
Very interesting question. Thank you.
Thank you.
Thank you. Our next question will be from Professor Chiranjeev Mitra.
Yeah, thanks. This question is for Ashok. So this is primarily because you hinted a lot of time that I can have it in the discussion session. So about the experimental techniques. So two things. One is here the electron is coupled to the nuclear through a hyperfine coupling, and you are actually doing the every measurement in the nuclear spins. So how do you actually so initially polarize the nuclear spins? First, of course, you polarize the electron spin, which is coupled to that. Now the thing is, you are applying this dynamical decoupling scheme or spin locking to the nuclear spin, which is basically in the RF frequency range, and the electron goes in the gigahertz range. So are you also applying pulses to the electron to make it stable? And so that is, I know, minute experimental details. So if you can throw some light on it.
Definitely. Yeah, indeed, you know, so as we kind of bury all these details because they are technically dense, but let me just, I have some slides on it, but I can tell you a big picture of how we do this. So the electron, in this case, this NV center plays the role to just initialize the nuclear spins, because while the nuclear spins have these amazing properties, very, very long T1, actually this is a very well-known problem in NMR, that if you just take a random solid, like calcium fluoride, you know, has a T1 of like multiple weeks if you don't dope it with electrons. And just as a historical aside, you might know that the first Nobel Prize for NMR came from Ed Purcell, and collaborators who got the Nobel Prize for showing the NMR of water. But simultaneously, actually, few years ago, there was another person in Sweden who was trying to build the NMR apparatus, but it chose to measure calcium fluoride instead of water as the first sample. And basically, the T1 was many weeks. So if you put the sample in a magnet, it takes a long time for the spins to even thermalize to the weakly Boltzmann polarized state. And so the signal was never present, although the apparatus was correct. So, so it's well known that nuclear spins have a very long T1. And what we use the electron for is twofold. We increase the polarization very fast, and we do this at low magnetic field. So the experiment actually starts off at low magnetic field, where we shine light on the electron in this NV center. We apply microwaves, but since we are at low magnetic field, the microwaves are applied at relatively very low frequency, like few gigahertz. And then the nuclear spins get very highly polarized. And then we actually rapidly move the sample into a high field environment. So we call this sample shuttling. Sample moves in under a second to 10 Tesla. And in 10 Tesla, we leave the electrons because their resonance frequency is very high, approaching hundreds of gigahertz. And we only apply pulses on the nuclear spins. So, so the experiment starts off at low field and goes to high field. And we move in between these two field centers. Hopefully this answers your question. And then because of doing this hyperpolarization process, the long T1, which is usually a problem, is no longer a problem. And because we can go back to low field and the T1 is close to 0 or very short, spins die very fast, and we can restart the experiment. We build everything ourselves, so it's an NMR magnet. We build our own probe, and then we have our own shuttling apparatus. And yeah, it's I've got some pictures, but yeah, large building effort, right? Rapid shuttling between the sample, two magnetic fields.
Okay. Another question from Prem Kumar, IMSC.
Hi, I'm Prem from IMSC Chennai. I work in open quantum systems. So my question is regarding the long coherence time that you discussed. So using your method, can your method also be extended to other physical systems other than NV centers like superconducting qubits or quantum dots, and also for amorphous material rather than crystalline material? Yeah. Is it very general? Can it be extended?
Yeah, definitely. So just say that this coherence time is a little loaded statement. So I would say that all we've shown is a long lifetime, and coherence means a little bit more, and I don't think we have that. So it's not like we can do quantum computing for 500 seconds, but for sensing, this is what you need. So it's the relevant time scale for sensing. Yeah, so the only ingredient we're using here, as Ranjit was saying, is a long T1, because T1 sets the overall universe of time that you have to play with. And if your T1 was a second, then whatever you do with some fancy pulse sequence, you can never beat a second. So these systems have just a very long T1. And the pulses are applied in the RF domain, and RF pulses can be made very, very close to perfect compared to, I would say, laser pulses, or so optical qubits have much more error. But yeah, so the same tricks can be done in many other systems. So I would point that IBM group had a similar experiment on their Josephson junction qubits. The T1 is much shorter, so they can show pre-thermalization. They can even show all these textures in their coupled qubits. The advantage they have is they can literally measure every qubit, and they can make different pulse sequences on different qubits, things we don't have access to. But their total time is very short in comparison. So I think we are about 10,000 times longer in time scale. But definitely, it's I think a very rich area of people are exploring at the moment.
So I use the word coherence time. I was talking about T2. It's not coherence time?
So T2 is coherence time usually, but here we are mostly getting lifetimes along some particular axes, and you can make the axes time dependent, etc. So I think the correct terminology is like T1 row, but this is a variant of T1 row. It's not exactly T1 row, but it's a T1 row is close to T1 row. Correct. So I mean, T1 row is the lifetime under continuous spin locking, and here we have interrupted spin locking. So I mean, we can talk about the semantics of this, but it's slightly different from a true coherence time.
Okay, so it's not as useful for quantum computing rather than sensing only.
So yeah, I think it's for quantum computing. The things you need are very different, right? So really, you need access to the individual qubits. And I think the way to go is error correction and the way people have formulated it. So here we are more interested in sensing. We want to be able to sense weak perturbations in a very sensitive manner, in a noise-corrected manner, etc. That's the primary purpose. And to your second question about crystallinity, yeah, indeed. I mean, these experiments work on crystals, also powders. So you don't need crystallinity. The system can be rather disordered. That's the advantage of these systems. And because of that, you can interface them with the real world. So we're literally putting nanodiamonds inside cells and really relatively dirty environments, and you can do similar experiments there. Doesn't work as well as if you have a pristine crystal in a vacuum chamber, but it works similarly.
Thank you.
Thank you. Any other? Yes, please.
How do you do the detection? So normally in NV Center we do ODMR, but how is your detection?
So in the experiments that I showed you today, so we also do ODMR, but I didn't show you things today. What I showed you today, we are detecting through NMR, classic NMR, but the spins are very highly polarized, so you can detect even smaller volumes that you would do with NMR. So NMR is just I would define it as a radio in a magnet. It's a small LC cavity, weakly coupled to the spins, very low Q factor, maybe 50 to 100. And yeah, you're just detecting while you're not transmitting. So, if that makes sense.
Thank you. Other questions or comments? Yes.
The first question I have for you is, if I want to demonstrate this pre-thermalization in real NMR bath, what are the what is the biggest obstacle I'll face there? Because to what you are doing here, so you have a large many-body system and actual bath is weak. Part of the system is your system and the rest of it is more or less like environment, and you're showing there. So
say the first part again. What do you mean real? Say again.
I mean to say that the system is interacting to the NMR bath, not a many-body system, and part of it behaving as a system and rest of it behaving as a bath. In the real T1, I meant to say that when pre-thermalization is happening, you're assuming that the T1 is very large. So actual thermalization, could it have this kind of bizarre behavior?
Yeah, so certainly you can't beat T1, right? So whatever is the T1 that sets the overall bound, and you can ask the interesting question whether you can actually control T1.
I was asking that in real thermalization, could it happen that the system settles to a pre-thermalization state for a long time and then it relaxes back, maintaining out some system?
Yeah, I think it's very specific, depends on the type of system that you have and what you're trying to do with it. So you can do the same experiment that I showed you, but instead of flipping the spins from X and working in X, you can go from Z to minus Z. And once again, then the true time scale is like T1, and then you can get a lifetime that is close to T1. I don't know if that makes sense. So it's, yeah, I just view it as, yeah, indeed, you have a weak overall interaction with the outside world. That makes it convenient to be able to observe. But the dominant decay is coming because you're creating states that initially don't commute with the Hamiltonian that you have under, that's naturally present. And you can modify the Hamiltonian. Now you start seeing this behavior, which is pre-thermalizing to that Hamiltonian.
Yeah, and just one small question based on your comments also on the NMR measurement that you talked about. So when this magnetization is precessing and it's inducing the current in my receiving coil, driving that current requires some amount of energy, right? Because there is some amount of resistance in that coil. That is coming from the actual magnetization system. Is that causing a continuous measurement or kind of collapse? Or
I mean, the actual data that we gather, it's more like a continuous measurement. Yeah. I mean, we don't see any spectacular collapse. But then, when you work with 10 to the power 20 spins, millimolar, and then suppose every spin they're in some coherent state, and then some fraction of them collapsing and going to the Zeeman state, and that coherence which is vanishing, maybe the coil and the spin they're entangled and getting transferred. These theories have not been worked out. So what I'm saying is completely probably Ravish. But we do not know. We do not know. All we know is the classical picture works very well. Magnetization rotating inside. So there is a periodic change of flux that induces a back EMF on the coil. We sit down with a potentiometer and look at that change. So it is nothing but a continuous measurement.
Thanks.
Yes, please.
Yeah, there's very weak back action, almost no. I think you can view a classical analogy to this experiments I described as ferromagnetic needles, that are, it's like a magnet that you set precessing, and you can do the same physics here, except here you would have like a frictionless needle, effectively, because the needle is precessing, we have something like 10 to the power of 12 oscillations. So it's like, in the classical analogy, it would be a frictionless, or very weak friction, levitating magnetic needle.
Once again, my question is to Francesco. So if we look at like the tradition, because all we are interested in, let's say when the system is interacting with the environment, in which situation I can have reduced system dynamics as CPTP map, no? Like completely positive trace preserving map. Well, and also to ensure that we are demanding that the extended system has to be Markov state and this kind of thing. No, but in reality, this is not the case. In reality, my environment can be arbitrarily correlated with the system. So in a sense, it kind of indicates that maybe the condition we are looking at may be too stringent. That means we need to even allow some kind of a non-CP map. We cannot do away with that, right? So is there any way for you to comment on this, like why we should be always restricting ourselves this reduced map to be CPTP? Why not non-CP? Francesco.
Thank you very much for the question. Yes, so actually this opens up the other way in which one can think about this problem, right? So in the exact case, this Markov condition, this Markovian condition was equivalent to CPTP reducibility. So now you can choose to, there is a branching now. So when this is not the case, you can say, okay, on one side I look at revivals. On the other side, I look at weakening of the CPTP condition. These are both, in my opinion, very well-defined problems mathematically. The only thing is that I don't see relaxing the CPTP condition as being more physical. And I tell you why. Because typically, in the situations I think you are thinking of, like what happens practically, typically in those situations, you don't even have a linear map for the reduced state system. And so rather than having a divide between completely positive reduced dynamics and non-completely positive reduced dynamics, the big divide is when you have reduced dynamics and when you don't have a map at all. And so I see, this kind of hierarchy that some authors suggest as a possible solution to the problem, this hierarchy of divisibilities, so that you have CPTP divisibility, P divisibility, and maybe, you go down up to, I don't know, weaker and weaker and weaker form of divisibility. I see this as a very mathematical, I would say, let me use the word, a little bit artificial problem. To me, it's more like fundamentally relevant, and I would say also physically relevant, are what kind of correlations are established during this evolution. But this is only my viewpoint, actually. But yeah, I don't know if this answers your question. But
yeah, actually the point is that whether we call it artificial or not, it happens. This is the point. But anyway.
Oh, no. But it happens, well, typically it happens that you don't even have a map. Like if you have absolutely no control on what is the system and what is the environment, so that any kind of correlation can occur, then somehow you should actually forget about even trying to define a reduced dynamics for the system alone. You should really take these two systems as evolving together. So what we have in mind typically is that you are in a kind of a weak coupling regime, sort of, no? That you have a system that you can call a system. Just the fact that you give it a name, you call it a system versus an environment, it means that you can at least identify more or less what is the system. And so this can be seen as a kind of a weak coupling condition that you can do experiments on the system. Otherwise, you know,
Yeah, I got it.
it's just a big melting pot, and you cannot divide the system from anything else, and then forget about doing anything.
So it would be a futile exercise somehow. It's because it would be just not possible to define a map.
Yeah, like, you know, if there are really correlations that you cannot control, then does it make any sense to draw a divide and call this is my system and this is my environment, even though I cannot control the way they interact? Perhaps no.
So the boundary cannot be drawn very easily.
Exactly, exactly. If you draw a boundary with words, it means that you should be able to draw the boundary also somehow with your physical operations. But if not, these are just empty words.
Okay, makes sense. Yeah. Thank you so much. Thank you so much.
Thank you, Manab. Thank you.
Any other question? Yes, please. So, here.
Hello everyone, I'm Shoilei from Aizen Mohale. I actually have a question to Professor Bhattacharya. So, right now, you just said something apart from the classical framework about the NMR detection, like some interaction between the spin and the probe. So, can you please elaborate? I mean, what you were saying?
What I'm saying is, what I was trying to say, that when we do ensemble spectroscopy, the coil that picks up the signal, we have a good classical picture for that. We do not have a good quantum mechanical picture for that. That's all.
But you were saying something about the quantum mechanics.
That I think it was a speculative. So, and maybe we can discuss it outside. It's still to be a kind of, you can think of this way. I mean, we have a lot of quantum coherences, a lot of spins are there. They're in the coherent state. And then we are picking up signal which is oscillating directly coming from this coherent state. So this classical picture must have some quantum analog that we should be able to write in terms of, you know, a little more quantum mechanical quantities. We do have a classical picture like how to write that in terms of susceptibilities and all, but we do not have a good quantum picture. That's all.
I know we do not have a good quantum picture. It is an open
question. Maybe,
but you were saying something, so that's why I'm curious.
I do not know.
Well, yeah, the NMR detection works on the principle of Faraday induction, and you can write this down.
Classical thing.
And yeah, so, you know, well, can you write down the quantum mechanical version of Faraday induction and the limit of very few? So I know some people are working on this topic.
Okay.
Any other question? Okay, there is one.
Can you hear me?
Yeah, we can, but still, please use the microphone.
Yes. So my question is, you have this pre-thermalization phenomena. Could it be some sort of phase transition, jamming-induced phase transition type of reason behind it? Like, is it a possibility?
Yeah, I don't know, to be honest. I don't know if it's a phase transition because I don't know if there's a boundary, and I don't know, it doesn't follow the properties that you would expect for a phase transition. And I don't know much about jamming phenomena too. I know something about it, but I don't know if it's that. So I'm happy to talk afterwards if you have some ideas. We have experiments showing the thermalization. You can actually watch it happening, and you can also model it with sufficiently large number of spins. Like you can take 20, 30 spins and do multiple, you do an ensemble average, and you also have to do an ergodic average, and then you can see it happening. But yeah, the microscopic mechanism of this pre-thermalization, I'm not able to articulate. So.
Thank you. Any other question? Okay, you have.
My question is to Francesco, sir. Sir, am I audible? Sir, I'm Shayan. Sir, my question to you is regarding the Markov and the non-Markov distinction. Sir, if we take a system, suppose we have a system and we keep it inside an environment or dip it inside an environment. Now, if we allow the system and the environment to interact, right? So, initially, we assume that since the system and the environment have just started interacting, so at time t equal to 0, they are uncorrelated. They are in an uncorrelated tensor product state, right? Now I let them evolve in time under some kind of Hamiltonian. Under the interaction Hamiltonian on what? Under the interaction Hamiltonian. Then what I do is, I trace out the environment and find out the state of the system. And I repeat this. And from the state of the system that I obtained at multiple times, I find out some properties like L1 norm or concurrences and all those things. Right?
Sorry, what do you find?
L1 norm. Suppose I'm finding out L1 norm. Okay.
L1 norm?
L1 norm of the system, reduced system, after interaction. L1 norm, that's the coherence. I'm finding out the coherence of the system after interaction with the environment at each time step. Now, if I see that there is some kind of, there is a periodic revival of coherence with time, can we say that the system and the environment follows non-Markovian dynamics, because I have not assumed the one-Markov approximation here?
Okay, so I would say that being Markovian or not is a property of the reduced dynamics. I mean, the system and the environment, a unitary evolution is always, in particular, a Hamiltonian evolution is always Markovian, right? Because you can divide, the Hamiltonian generates the time translation group, and so you can divide the time in as many parts as you like, and still this would be a Hamiltonian evolution. So the Markovianity property, or being non-Markovian or Markovian, is a property of the reduced evolution of the system only. So now if you see coherence that fluctuates, that definitely tells you, well, now I don't know exactly what kind of measure that you have in time. These things are also dependent on how you measure these revivals. That is a completely different problem that people have been defining revivals according to different measures. But I would say that a revival is a good measure, that an information measure is a good measure of a revival if it satisfies the data processing inequality, right? Because you wanted, if the evolution is Markovian, this would not have any revival. So whenever you see a revival, then you witness the non-Markovianity of the evolution of the system. And therefore, you know that there is an environment somewhere around with which the system is interacting that keeps memory of the past of the system. And so these are this kind of echo effect, this Loschmidt echo effect, sort of. No? So yes, definitely that would be a witnessing of non-Markovianity.
The environment size has been kept finite. It's not infinite.
Yes, yes. Typically, you know, this Bohr-Markov approximation, they always hide behind some kind of an assumption that the bath is so much bigger than the system that can be actually assumed to be infinite. And so you can imagine that you have a kind of, every time the system interacts with the environment is so big that it's interacting with a fresh subsystem of the environment. So this is what keeps this, that kills the memory effectively, right? So, but when the environment itself is a finite system, then memory effects or absence of memory effects, I would say, it's just an approximation. And sometimes if you have very good experimental devices, you can actually see these echoes and you can witness it actually.
Sir, in this regard, even in finite environment, we can observe Markovianity if we adjust the coupling between the system and the environment. It has been shown mathematically, but there was no physical explanation given. I had seen a paper where they had shown that if we can control the system environment coupling for finite size environments, then we can transition the system from Markov to non-Markov. They had given some examples. If the coupling constant is a polynomial function of time, then although the system is finite, although the environment is finite, we will observe non-Markovian dynamics.
Even if the system is the environment is finite, you would observe.
Yes.
Markov dynamic, I think.
Yes.
That's
that depends on the coupling constant. There was a paper by Shagnik Chakraborty, I think so.
Okay. Yes, there are papers in which they can actually control to switch on and off this non-Markovianity effect. And for example, with respect to what I described before, it would be interesting if one could switch on causal and non-causal information backflow. So now you have 3 levels. You don't have 2 levels anymore. It's not just Markovian and non-Markovian, but you have Markovian, then non-causal revivals, and then you have genuine backflows. So now you have 3 levels that you can cross, and maybe it would be nice to have a switching among these 3 levels of non-Markovianity.
Thank you, sir. And we have a comment here. Yes.
Yes, so I have a quick comment, addition to what Francesco said. So revival of coherence does not certify something to be non-Markovian. For example, you just think your spin is up and you apply, let's say, some magnetic pulse along X. Obviously, it will increase the coherence, no? But it's still a unitary process. What actually means for non-Markovianity is revival of correlation. It's not coherence. So this is just to first correct this part. Second part, what you were talking about the dimension. The way we define Markovian or non-Markovian, it really does not care about the dimension of the environment. It only comes when you look for some dynamical equation like Lindblad or certain approximation to be satisfied. For example, for any d-dimensional system, if I want to design a map or simulate a map, just d-square dimensional environment is sufficient. Okay? So it really does not matter. It's the question of like whether the correlation is coming back or forth. Okay? It may so happen. Let's say I have one system and then I have some other system and I am going with like global unitary. In certain process, at a certain point, obviously it may be a periodic evolution. The correlation increases, then the correlation decreases. So the moment the correlation decreases, the local map can still be defined. But when it increases, you cannot. So it's a more question of revival of correlation, in that sense, data processing inequality.
Sir, in this regard, sir, maybe, what if my system is composed of a single body?
Lost meaning, I mean, just sorry to interject, basically, we are just meaning completed our hour of discussion. So you can finish what you're saying, please. Okay.
Sir, my question to you is, what if my system is just a single particle?
It's perfectly fine.
Then how do you have how would you measure the correlation? Would I take an ancillary
particle,
system?
You can always consider a reference connected to it.
Ancillary
and with
system.
respect to that, you will have.
Okay. Then I have to look into ancillary systems.
Yes.
Okay, sir. Thank you, sir.
Okay, we would like to thank everyone, but we have a small question. Okay, one last question. Definitely, this is the last one. Yes, please.
Thank you, Rangit sir, for allowing me. It's a small question. My question is for Francesco sir. Sir, in your talk, you presented this inequality where the correlation between R and Q at a future time is lesser than the correlation between R and Q at the past time. So, does this inequality somehow correspond to the H theorem, which indicates that the total entropy of the system and the surrounding will tend to increase? And if I consider the inequality that you presented in terms of the correlation, if I consider that as my axiom, can I prove the H theorem of the entropy?
Okay.
Yeah.
Very nice question. These are even though they look similar, these are two different questions. First of all, because typically the H theorem, you want to prove the H theorem in an isolated system. So there is no environment there, there is no reference there. It's just a system evolving of unitary evolution, and the mystery is why the system thermalizes, even though there is no bath with which it can thermalize. Whereas here, there is the environment around. So it's really a system that is exchanging everything with this environment. There are no constraints in general on this interaction. And so I would say that we are in two different ballparks, right? Of course, there have been proposals. I mean, the data processing inequality looks an awful lot like the second law of thermodynamics. No, there is something that keeps decreasing. Yeah, the correlations keep decreasing. In the second law is the entropy that keeps increasing, but you have a monotonic behavior of some quantity. And there are like information theoretic formulations of the second law. There is a famous one by Cover, the cover of the Cover-Thomas book in information theory, where he identifies the data processing as a kind of computational second law. But I would say that if you dig a little bit below the surface, then the analogies between the two are seems more of a coincidence rather than having anything very deep in connection. But yes, it's definitely something that is very tantalizing and good question. Yes.
Sure, thank you. But if we consider my environment as well as my system to be together considered as an isolated system, in that respect, could we draw some analogy?
Then you should change your measure of entropy, because the mutual information would not change. So if you consider system and environment together and they evolve unitarily, these like quantities based on von Neumann entropy don't change. They remain the same. That's why von Neumann himself in his book said that if you're interested in describing the second law of thermodynamics, you should not use my entropy. He says you should not use the entropy I defined 2 pages before, but you should use a different quantity that he goes on introducing, and he calls it macroscopic entropy. And it's a different thing. It's closer to Boltzmann entropy somehow. So it's a kind of a coarse-grained entropy. Otherwise, if you do not do coarse graining, if you just use von Neumann entropy and measures that are based on von Neumann entropy, you will not be able to prove any second law of thermodynamics for isolated system, because entropy does not change.
Absolutely. Thank you, sir.
Okay. So with that, I mean, we stop the discussion. I mean, and we would like to thank both the speakers, Francesco and Ashok. You did wonderful job and gave us
very much
very nice overview of what is happening at the forefront. And we have a small tokens of gratitude for you.
Okay.
So
thank you.
Ashok's yours.
Okay. Is this the coffee mug, or is this a... Okay.
Yeah.
Okay.
If you can point to us, me. Well, Francesco, this is for you. I can't give you here, but this is for you. We'll send it to you. We'll have it.
So it's a token for me to come back to Kolkata very soon.
Yes, please. We'll be more than happy to host.
Thank you.
Yes.
Thank you very much.
Okay, so that is the end of the session here. Now it will be the poster session. So everybody is requested to go there, and following that, it will be dinner. So now all the poster presenters are supposed to be close to their posters. Yeah, and there is coffee at 6. Yeah. Yeah. Okay, here.
Thank you, Francesco. We now switching off this. Yeah.
Okay, thank you very much.
Yeah,
and apologies
hope
again for all the inconvenience, this caused, and
no problem, no issue.
I'm very sorry for not being there. I really wanted to be there, and looking at you now really makes me